today we embark on the most important part of high school physics, work-energy theorem. Because without work, there's no change in energy. Without energy, no work can be done. Thus, nothing can happen without the work-energy theorem. That makes it the most important thing in high school physics. We would have nothing to study were it not for energy. Okay, so this is a concept that comes back over and over and over again throughout high school physics. Okay, it comes through like 3 or 4 times in physics 20, and it comes through probably over a dozen times in physics 30. Okay, energy is the reason things happen. Okay, so without it, there's no physics and there's no nothing. Okay, so we need to understand that work-energy theorem says that work and energy can be equal, but that one cannot exist without the other. Okay? Understand kinetic and potential energy, and understand the relationship between force and work. Okay? So very simply, work-energy theorem says that work is a change in mechanical energy. That should be familiar because we talked about it on the first day. And we talked about work and energy and how heat is a transfer or a change in thermal energy, and work is a transfer or a change in mechanical energy. We talked about that earlier on in the unit. Okay? Now we're going to look at this from a mathematical perspective. Okay? So work is a change in mechanical energy. If I do work, the energy of something else and myself will change. Okay? So that's the definition of work. Okay? Work is a change in mechanical energy. Energy is the capacity to do work. See how you can't have one without the other? Okay? Work is a change in or a transfer of mechanical energy, and energy is the ability to do work. In other words, if you have no energy, can you do any work? No. You probably said that to your parents this morning when they go shovel the driveway, and you're like, I have no energy for that. I mean, you did. Okay? You have energy, but you just didn't want to. I didn't. It's May. I don't shovel in May. It's just a rule I have. I don't care how much it snows. It'll melt. Okay? And I know that reasoning could go through all the whole year. Eventually it will all melt, but in May it's good. Okay? So if you don't have any energy, you can't do any work. In other words, I can't transfer energy to something else because I can't give away what I don't have. Okay? If I don't have any energy, and work is a transfer of energy, I can't do any work because I have nothing to transfer. Okay? So, for example, can this desk do any work? No. It has no energy. It's not moving, and it's on the floor, which means it can't fall either. So it has no ability to do any work. Okay? Because it has no energy. It has no kinetic energy. It has no potential energy. Okay? It just can't do it. Right? So work and energy have this very kind of, they have a very strict relationship, let's say. The one cannot exist without the other. Okay? And you can't do one without the other. Okay? It's kind of like the chicken and the egg. Well, it's a bad example. Which came first, the chicken or the egg? The chicken. No. Eggs. It's a definitive answer. Birds evolved from reptiles. Reptiles lay eggs. Therefore, eggs came before chickens because chickens are birds. True story. I don't know why everyone's like so enthralled with which came first, the chicken or the egg. It's clear. It's abundantly clear. Right? It's like if a tree falls in the forest, does it make a sound? Absolutely. I don't have to be there to hear it to know it's going to make one. It's physics. Physics answers all the interesting questions. Just keep that in mind. Okay. All right. So work's a change in energy. Okay, which means work is our final mechanical energy minus our initial mechanical energy. That's what delta means. Delta always means change or final minus initial. Okay? Now, if I'm going to do work, let's say I've got energy and I'm going to do work. How do I do work? Like if I want to do work on this desk, what are some ways I could do work on this desk?
Push it.
I could push it. Okay? I could lift it. I won't. I'll hurt my back. But those are ways that I could do work on the desk, because any one of those would change the energy of the desk, and probably the surroundings as well. Okay, I'm not going to lift the whole desk, but if I do this, okay, does the desk have energy now? Yes, it does, because if I let it go, it'll fall. Okay, and that'll do work. It'll make noise, it'll startle people. So yeah, once I do work, it has energy. Now, when I did work, it required me to do something. I had to lift, okay? If I lift, I'm exerting a force, okay? And that force has to result in movement. So, force times distance will calculate the amount of work I've done in joules, okay? And that will change the initial energy from 0 to some final value. And I will have done work because I have changed the energy of the desk. Okay? And the same would be true if I pushed the desk or dragged the desk along the floor. Okay? If I drag the desk along the floor, I'm still exerting a force, I'm still pushing it or pulling it through a distance, and I'm changing its kinetic energy because I made it move. Okay? If I just lift it like this, what kind of energy does it have? Potential energy. Okay? So work can change either one. In fact, it can change both at the same time. If I picked it up and threw it, which I wouldn't do, okay, it would have both kinetic and potential energy. Okay? Everyone all right with that idea? How work and energy work? Okay, so energy, like motion, is a measurable quantity. Specifically, energy is a measure of an object or a system's capacity to do work. Okay, that is the definition of energy. Okay, and then we have the definition of work here as well. Okay, the classic mousetrap is a prime example of work and energy. In its current condition, does the mousetrap have energy? It has potential energy, yes. It has elastic potential energy, okay? Because the spring has been compressed, okay? When you load the mousetrap, okay, so you pull back on the killing bar, that's actually its name, it's appropriate, okay? So you pull that back, and then you hook the trigger hook, okay, into the trigger. This is the trigger hook, this is the killing bar, okay? When you pull the killing bar back, you change the shape of the spring. When you do that, you exert a force through a distance, okay? You put potential energy into the spring, okay? When the trigger is triggered, then the spring will release its potential energy, and the killing bar will gain kinetic energy. And it will go very fast, and then it will do work. Okay. It'll, do work. Okay. It'll make sound and all that other stuff that it does when it's triggered. Okay? But it's a perfect example of having something get work done to it and then have energy, and then be able to do work itself because it has energy. All right, so everyone follow the transfers? Okay, now work energy theorem, okay, and the transfer of energy is an important part of lots of sport science. Okay, this is like a stop motion shot of somebody doing a tennis serve. Okay, so they throw the ball up in the air, okay, and you can see the ball kind of moving up here, and then you can see the racket, okay, hitting the ball. Now you can see the ball moving away this way. Okay. Now, why do they use a racket and not a paddle?
Is it because the racket is able to transfer energy better?
A little bit. Yeah, it does certainly have to do with that, okay, because it has strings which are elastic, okay, as opposed to a flat, solid face like a paddle.
Because it's more aerodynamic.
Yeah, it's way easier to swing it fast. Right? It's lighter, air goes through it better because it's a hole, it's a net as opposed to a paddle. Okay? So all of those things increase the ability of the person swinging the racket to do work. It's moving faster, so it has more energy. Okay? And this important part of the work energy theorem. Work is force times distance. Your force is kind of predetermined. It's based on how strong you are and probably to do a bit with your technique, how good you are at like swinging the racket accurately. Okay, so that part's kind of predetermined by the person swinging the racket. But the racket can affect the distance over which the force can be exerted. Okay? If this is just a paddle, if a racket's just a paddle, the ball hits the paddle and the ball compresses a little bit. Okay? And it stays in contact with the paddle for a short distance, maybe 10 centimeters, maybe 15 centimeters, and then it flies off of the paddle. But the racket, because it's a net and the strings are elastic, will actually allow, so if here's the frame of the racket, it'll actually allow the ball to sit in here as the strings go back. Okay? That means now it's going to be in contact with the racket for a greater distance, enabling me to do more work and transfer more energy to the ball, meaning I can serve it faster. Okay? I can serve it faster with a racket than I can with a paddle for a number of reasons. Okay? The only advantage the paddle has is that it's more massive, and mass does also contribute to energy. But speed is more important, which is why most sports implements that need to be swung most are lightweight. Okay? The same is true for modern hockey sticks. Okay? I don't know if you saw this the other night, because I was watching the Oilers game, and Ryan Nugent-Hopkins scored that goal with a broken stick. Okay? His stick actually broke, but there was enough of it holding on that he was still able to score. Okay? So the modern hockey stick is made out of composite materials, graphite, carbon fiber, okay, things like that. As a result, modern hockey sticks are incredibly flexible. Okay? When I was a kid, you could get a Sherwood, which was made out of a piece of tree. All hockey sticks were made out of pieces of tree back then because it was the Stone Age and that's what we had. Okay? Now you guys have these modern composite sticks. So a modern composite stick can do this. Okay? It can bend and flex. Okay? Whereas a typical wood stick had a little bit of flex. It might be able to flex about that much. Okay? So when it flexes, look at the distance over which I can exert force on the puck compared to a wooden stick. Okay? All other things being equal, if I give a wooden stick to a professional hockey player and a composite stick to a professional hockey player, they are going to shoot the puck faster with the composite stick. Okay? If they hit it in exactly the same way, if they do a one-timer with both of them, they're going to hit the puck way faster with the composite stick. Okay? Because it can exert that same force over a much greater distance. That's why you see basically nobody playing with a wooden stick anymore. Okay? That sort of makes sense? Okay? Lots of sports science is based on this exact idea. In fact, a lot of sports safety equipment is based on this exact idea. Okay? If we can make the distance over which a force acts on somebody's head, okay, like less, okay, we can reduce the amount of work that is done. Okay, sorry, more. We can reduce the amount of work that's done. But yeah, we can do all of these things. Okay, like we can do this with golf clubs. Okay, golf is the same thing. They've made clubs lighter. They've made the shafts out of more flexible materials. They've made the ball softer, so that the ball sits on the face of the club for a longer distance, and as a result, you can hit it further. Driving distance now in the PGA is way further than it was 25 years ago. Okay, when hitting a ball was the same as putting a rock on a tee and swinging at it. Okay, now the balls are much softer, and that allows them to transfer energy better. Okay? About the only sport that hasn't embraced this is baseball. Okay? Baseball is still swinging a chunk of tree at a piece of horsehide. Okay? Now, granted, baseball has sort of embraced other sports science. Their approach has been more biological than it has been physics related. All right, so work is related to the force acting on an object. Obviously, the harder you push something, the more work you're going to do. Okay? It's the same for a bow and arrow. A bow and arrow is a classic work energy theorem example. As I draw back the bow, I exert a certain amount of force. Okay? The more force I exert, the further back the bow will be drawn. Am I doing work on the bow when I do that? Okay? What kind of energy is being stored in the bow? Potential, yeah, elastic potential energy. Because the bow wants to snap back to its original shape. I've pulled the ends together and changed its shape. Okay? When I release it, obviously the bow's stored potential energy is released and the force is exerted on the string, which is attached to the arrow, and it shoots the arrow forward, transferring that energy to kinetic energy, and the arrow flies out of the bow. Okay? Everybody all right with that? Okay, mass can also affect not so much the amount of work done, but the amount of energy, okay, that is either required or produced, okay, because a more massive object will require more work to get it going. Okay? So as an example, when you try to stop in a car, you apply the brakes and the brakes turn your mechanical energy into heat. Which stops faster, a small car or a semi-truck? Small car. There's less mass. There's less work to do because it has less energy. Even if they were going the same speed, it wouldn't matter. There's just less mass to stop with the small car. Okay? So if you're driving, something that's got a lot of weight or it's a lot heavier, you have to keep that in mind because you're not going to stop as quick. Okay? You have more energy based on how much mass you have. Okay, so there's this idea here between force, mass, and acceleration. It's Newton's second law. We don't talk about it very much, but it's still important to recognize. Okay? So I've got this guy here with his golf club and golf ball, and when he swings as hard as he can exert this much force. F. That's how much force he can exert. When he swings the golf club at the ball, he's talking about a very, very small mass. So when he hits the ball, his force and that small mass produce a huge acceleration. Okay? The ball's velocity increases incredibly. Now, if for some reason he decides to try a similar thing, but this time he's going to wind up and hit a truck, the results are going to be a lot different. Okay? He's still got the same force, but now we're talking about a huge mass, okay? Which is going to result in a much smaller acceleration. In the real world, is that truck going anywhere when he hits it with the golf club? Even if it's in neutral? It's not. Does that mean he doesn't do any work? Work's a transfer of energy. If he hits the truck with the golf club, does he still do work? Absolutely. Okay? And there's a couple of ways I'll know that. If I'm standing, let's say, in front of the truck, with my hand on the truck, first off, I'll hear it when he hits the truck. Sound is a form of energy, and he produced it by hitting the truck. That counts as work. Okay? If I'm touching the truck when he hits it, will I feel when he hits it? I'll feel the vibration in the truck, right? I'll feel the impact pass through the truck. Well, that means he moved every single particle in that truck. They just didn't all go together. Okay? The truck didn't move. If he did this on a perfectly frictionless surface, the truck would move. Ever so slightly. Okay? But it would. Okay, is that making sense to everybody? The effect kind of mass there? Okay, so motion doesn't just mean the movement of an object. It can also mean a change in shape. Okay? I do work if I compress a spring or I stretch a bungee cord, okay, or something like that. I'm not making them go faster or anything like that, but I'm changing their shape, and that counts as work. Okay? If I, put a dent in the board, okay, by punching it really hard, I know that I don't do that because that's crazy. Okay? But if I did, would that count as work? Sure. I've changed the shape of the board and probably the bones in my hand too. Okay? All counts as work. Okay, so work and heat. We talked about this the first day, so this is just review. Work and heat are both transfers of energy. Work's a transfer of mechanical energy. Heat is a transfer of thermal energy. Okay, so they both transfer energy. We're concerned here with just work, the transfer of mechanical energy from one object to another. Okay. Okay. Gravitational potential energy, okay, is possessed by any object that could do what? Fall. Any object that can fall has gravitational potential energy. Okay, so anything perched on top of that filing cabinet has gravitational potential energy. Anything lifted off the ground has gravitational potential energy because it can fall. Okay, now, let's say, and this is completely hypothetical, I'm walking down the street in Calgary in one of those construction zones, you know, where they usually build the protection over the sidewalk. Okay, let's say that I'm walking through there, but they haven't got the construction protection done yet. And I hear somebody yell and I look up. Okay, and when I look up, I see a hammer and like a screw. Okay, and they're both falling. And I'm gonna get hit by one of them, but I have a choice. Okay, I can move one way or the other. I'm not gonna be able to avoid them both. Okay, but I can avoid one of them. Which one should I let hit me? Why? It's smaller, right? So one of the things that can affect your gravitational potential energy is mass. The bigger something is, the more gravitational potential energy it will have at the same height. Okay? What if it's two screws? One was dropped from the first floor, the other was dropped from the 10th floor. Which one has more energy? The one from the 10th floor. So height can affect how much gravitational potential energy an object has, the height it's dropped from or perched at. Okay? And the last thing that can affect gravitational potential energy is gravity. Now on Earth, that's always the same value. It's 9.81 meters per second squared. Okay? So that little g there always stands for 9.81 meters per second squared. So you've got that on the back of your periodic table as a useful constant. Okay? It's always there, acceleration due to gravity. So, gravitational potential energy is equal to your mass times the acceleration due to gravity times the height the object is falling from. Where did the object get its potential energy from? Why does an object above the ground have potential energy? How did it get it?
Because it could fall.
It could fall, but why can it fall? How did it get there? It got moved, right? Somebody did work. Exactly. Okay, somebody did work. That means they carried it up there somehow, lifted it up there somehow. Okay? All right. So that's the stuff that can affect gravitational potential energy. Let's talk about a theoretical exercise. Actually, I might have a diagram of it. I do. Okay. So, gravitational potential energy is the potential energy of an object due to its position. All forms of potential energy are described with respect to a chosen reference point or condition. What's a logical reference point to measure gravitational potential energy from? The ground, yeah. Okay, that's a logical reference point. For most things, it's measured from a height of 0 meters, okay, ground level. Okay, diagram on the left. Those two blocks are the same mass. They're both going to end up sitting at the top of that ramp. One person is lifting it there, the other's pushing it up the ramp. Who does more work? They do the same. Same amount of work. Because at the end of this, both rocks are right here, not moving. Which means at that point, they both have the same amount of gravitational potential energy. They're the same mass, they're both on Earth, where it's 9.81, and they're both the same distance above the ground. Okay, so it doesn't matter how it gets there. It takes the same amount of work to get it there. Okay, that's the purpose of a ramp. Okay, an inclined plane is the simplest machine because it makes work easier. It cannot make less work. That is impossible. To get something to the top of that ramp means it's going to have a certain amount of energy when it gets there. That's the amount of work I have to do, okay, regardless of how I get it there. But using a ramp means, if we're looking at this from a work perspective, who exerts more force? Yeah, the guy lifting. Okay, remember, when this is all said and done, the work done to both of these rocks is the same, because the energy they will have at the top is the same. Work is a change or a transfer of energy. So they will both have done the same amount of work. That means this guy, because he's doing the work over a shorter distance, okay, has to exert more force than this person does over a greater distance. Okay? So the purpose of an inclined plane is essentially to make it a force multiplier. It means I can do the same amount of work using an inclined plane as a much stronger person can do deadlifting something. Okay? I don't have to use as much force. Okay? But I have to use that less force over a greater distance to do the same amount of work. It's how the Egyptians built the pyramids. Okay? They didn't have help from aliens. Okay? They had slaves and sand. And you can make really long ramps out of sand. Okay? And what they did is they just built them so that they wrapped around the pyramids. And then they just pushed the blocks on, like, palm tree trunks up the ramp. And every time the palm tree trunk would come out the back, they'd move it to the front and just keep going. Okay? If you make those ramps long enough, they're not very steep. Okay? And because they wrapped all the way around, they could make them longer and longer and longer. Okay? And get the stuff up to the top. Yes. Okay. In this example on the right, I've got these two masses, and they're connected by a rope over a pulley. If I pull this mass back, this mass will come up. Yes? Okay. Did I just do work? Okay, I did. I exerted a force through a distance. I pulled this back. What kind of energy does that give to the system? Gravitational potential energy, because I'm going to be holding this thing. It's not moving, but it can fall if I let it go. Okay? If I let it go, gravity is going to pull on the 5 kilogram mass. It's not going to pull on the 3 kilogram mass because it's sitting on something. Okay? But it is going to pull on the 5 kilogram mass. Okay? And that's going to take the potential energy and turn it into kinetic. But it's going to change the kinetic energy of both, because the 5 kilogram mass is pulling on the 3 kilogram mass when they start to fall. Okay? It's not going to create energy. The energy will be split between the two masses. All right. So that's the formula. Is that going to be fairly easy to manipulate? Since they're all in a row and all being multiplied, if I want to isolate something, all I have to do is divide off the other two things. Okay, over to the other side. So it's super easy to use. Okay, so EP is the gravitational potential energy of the object in joules. The units for energy are joules. Okay, M is the object's mass in kilograms. G is the acceleration due to gravity. On Earth, that's 9.81 meters per second squared. And H is the object's height above the ground in meters. Okay, those units are really important. Okay, here's why. A joule is a kilogram meter squared per second squared. That's the base units for a joule. We just call it a joule because it's merciful. Okay? We don't have to say kilogram meter squared per second squared all the time. Right? But this is why this formula works. It's kilograms times meters per second squared times meters. Kilogram meters squared per second squared. That's the units for a joule. So if you were given a time in hours, or you're given a height in centimeters or kilometers or something like that, you're going to have to convert it to meters. And if you're given a mass in grams, you're going to have to convert it to kilograms. It doesn't happen very often, but just in case. Okay, so if we have a 3 kilogram box and we lift it to 1.5 meters above the ground to put it on a table, can we calculate the amount of potential energy it would have at that position? Yes. Okay, and all we'd have to do is go m times g times h. So we take the 3 kilograms, multiply it by g, multiply it by h, and we would find that the gravitational potential energy of that box would be 44.1 newtons. Or it's not newtons, sorry, joules. Questions on that one? Okay. I want you guys to try, oh, never mind. I put the answer on there. Don't try this one, we'll just go through it. Okay, so I have a 55 kilogram diver standing on a diving platform that has and there they have a potential energy of 5,400 joules. Okay, we want to find the vertical height of the platform. So I'm looking for h. I have EP, I have m, and I have g. So to get h by itself, I'm going to divide both sides by m times g. So I'm going to do this. Okay, that'll leave me with h. Then I plug in my numbers, 5,400 joules divided by, okay, 55 times 9.81, all enclosed, otherwise your calculator will do order of operations. Okay, that gives me 10 meters. So they're standing on that 10-meter platform. Okay, let's take a 5-minute break. And then I'm going to talk about kinetic energy and show you a couple of cool videos. Okay, if an object has potential energy, can the potential energy do work? So, like my water bottle is perched right on the edge here. Can its potential energy do any work? It has potential energy right now. Can it do any work? Not unless it what? Right. And when it falls, its potential energy is going to get converted into kinetic energy. Kinetic energy does work. Potential energy doesn't. Okay? Potential energy is the potential to do work. It's kinetic energy, the moving objects that actually do work. Okay? So that's something that's important to keep in mind. So let's say you want to break boards or bricks or something like that, okay, with your bare hands. That's a cool thing. Okay? It takes a lot of training though. Right? You or I couldn't just walk up even if we were told exactly how to do it and break a bunch of sidewalk blocks. Okay? We would certainly break our bones if we tried to do that. Okay? The people who do this train for it. Okay? They break lots of stuff with their hands, but not like a lot of it at one time. And what that does is every time they hit something, they cause microfractures in their bones. And then those microfractures heal and the bones get more and more dense. So somebody who's used to breaking bricks or wood with their hands or arm or knees or whatever will have a higher bone density than you or I would, okay, by the nature of what they do to train. It's actually why they tell like elderly people who are getting osteoporosis that they need to walk more and that they need to do more weight-bearing exercise. If they just walk, they'll cause little microfractures in their bones that will make their bones a little bit stronger, as opposed to if I just sit around, my bones will get less and less dense. Okay? Astronauts have this problem. They go into space and they're in zero gravity, their bone density plummets. Okay? When Chris Hadfield came back from the International Space Station, his bone density was that of like a 70-year-old. Okay? And that was with all the exercise and all that stuff that they do. It's just no substitute for constantly being pulled into the floor by gravity. Okay? That just does wonders for your bones and for your muscles. So, if I'm going to do this kind of work, obviously I need to have a lot of kinetic energy. Okay? My hands or feet or whatever it is I'm using to break the stuff has got to be moving very fast. That way I can exert a lot of force and make these things break. Now, I don't know if you can see in this picture here, but between each one of these boards, there's a little spacer. Why is that important?
Because if they're all together, they're like no room to move, so just all the energy would travel through the holes.
Yeah, and unfortunately be like reflected back on the person. Okay, so I'm not saying that breaking a stack of boards like this is easy. but breaking each individual board is not that huge of a feat of strength. And if you space them, you're actually just breaking a lot of little boards. If you put them all together with no spacers, you're breaking one really thick board, or not breaking any boards. Okay? The thicker it gets, the harder it's going to be to break it. You have to give room for the first one to kind of give away so that you can move into the second one, and so on and so on. Okay? So there is a bit of a trick to it in that you have to have those spacers there, otherwise you're breaking a telephone pole. Okay? And that's not going to happen. Right? So I'm going to show you a few videos here of people breaking stuff with their hands, because it's impressive. Okay, so the key thing here is that it's kinetic energy that does work, not potential. Okay? And the faster you get something going, the more work it can do. Okay? So potential energy of an object gets released, the object often begins to move, and it's moving objects that do work. A falling hammer drives nail into wood. Moving molecules in hot steam can turn turbines. Moving air, wind, can turn wind turbines. Okay? Moving molecules in a sound wave can make your eardrum vibrate. Okay, so all of those things are things that possess kinetic energy. Okay, so a moving object has kinetic energy. Okay, when a solid object moves, all of the molecules move in unison. Unlike that example with the guy hitting the truck with the golf club, okay, all of the molecules didn't move in unison. They all moved randomly, which is why someone at the front could feel the vibration of the truck, but the whole truck didn't go together. Okay. So the kinetic energy of such an object is called mechanical kinetic energy because it's all moving as one. Okay, so even when molecules are not physically attached to one another, they can still move together, like air molecules in wind. Okay, obviously we've seen, especially over this past year, okay, how much kinetic energy and how much work wind can do. Okay, I mean we've had tons of wind warnings and triple-digit wind speeds. Okay, this year more so than usual. Okay, we actually had where we keep our trailer. They had wind speeds of 160 kilometers per hour one day. Okay, and they actually called us up and said, "You need to come down because your trailer's off. It blocks." Okay, we were lucky. The jacks had just twisted, okay, and our trailer wasn't actually on its side like several other people's were. Okay, the wind just comes in from the side, and it'll tip over semi-trucks driving along the highway. I don't know if anyone saw that video on the Weather Network shortly after that, right near Stavely, okay, which is about 100 kilometers south of here or so. Okay, just right along the highway, and you can see the truck just started to lean over one. Okay, you got all those molecules of air moving together. Okay, they can exert a lot of force because they actually represent a lot of mass as well as a lot of speed. Okay, the same mass of air moving at 10 kilometers an hour, you don't even notice. But when it moves at 160 kilometers an hour, it's suddenly able to do a lot of work. Okay, and the reason for that is the formula for kinetic energy looks like this. 1/2 mv squared. Okay, so that means that the relationship between kinetic energy and mass is linear. That is, if I double the mass, I'll have twice as much kinetic energy. But the relationship between speed and kinetic energy is exponential because speed is squared in the formula. So if I double the speed, I don't have double the amount of kinetic energy. I have 4 times the amount of kinetic energy. If I triple the speed, I have 9 times as much kinetic energy. Okay, so kinetic energy and speed, and thus the work that something is able to do, have an exponential relationship. And this is something that's super important for everyday life, especially if you're getting your driver's license. Okay, because it's something that they don't really communicate very well in driver's ed. And that is the exponential relationship between speed and energy, and as a result of that, stopping distance. Okay? If I go 30 kilometers an hour through a playground zone like I'm supposed to, my car will stop almost instantly. It's not possible to stop something instantly, but almost instantly. If I double my speed, it'll take 4 times as far, for me to stop. Okay? Because of the exponential relationship. So here's something they won't show you. The amount of work needed to stop your car is equal to the change in your car's kinetic energy. We want it to go from whatever value it has because it's moving to what value? If you're trying to stop, we want your kinetic energy to be 0. You just want it to be gone. We want it to turn, your brakes turn it into heat and sound. Okay? So your brakes are going to do work. They're going to exert a force through a distance. This is your stopping distance. It's the distance over which the work has to be done to take the kinetic energy away from your car. Okay? And we know that change in kinetic energy means your final kinetic energy minus your initial kinetic energy. Okay? Now, your final mechanical energy, as we said, because we're stopping, is going to be what? 0. Okay? So really, the work that your car has to do, or your brakes have to do to stop your car, is equal to your initial kinetic energy. So it sets up like this. Work equals your initial kinetic energy. If I want to calculate how far it'll take me to stop, what do I have to do with force? Divide it over. Right, I just need to manipulate this equation so it looks like this. Now I'm solving for my stopping distance by taking the energy that I have and dividing it by the force my brakes can exert on my car. Okay, so let's say your average braking force is probably around 8,000 newtons, we'll say. Okay, around 8,000 newtons. Let's say the mass of an average car is about 1,500 kilograms. And if I'm going the speed limit, what's the speed limit in the playground zone? 30 kilometers per hour, which is about 8.7 meters per second, because we have to have it in meters per second. So we'll just quickly calculate. I think it's 8.7. Sorry, 8.3. Okay, so we're going to be traveling at 8.3 meters per second. So if I plug in all these values, I'll be able to calculate how far it'll take me to stop going the speed limit. Okay, so the kid runs out in front of me in the playground zone, just like on the sign. Right? Okay, so D equals 1/2 times 1,500 times 8.3 squared, okay, divided by 8,000 newtons. Okay, it's going to take me 6.5 meters. Okay, 6.5 meters to stop. So from the door frame here, that's how far it'll take me to stop. Going the speed limit. Okay, 6.5 meters. That's not too bad. As long as the kid doesn't run right out in front of your car, you'll be able to stop. And even if they do, you'll be on the brakes and you'll reduce your energy to the point where you are non-lethal, okay? Which is important, obviously. That's why there's a 30-kilometer-an-hour speed limit through a playground zone. Now, let's say you're an idiot, and because you're not, but we're going to theorize here just in case. Okay? Let's say you're going 60 through the playground zone. Not that any of you would do that, because you all have way more sense than that. Okay? 60 divided by 3.6. Okay, 16.67 meters per second. So if I do this same calculation now, okay, but I substitute in double this, how much further is it going to be?
Did you say 4 times?
4 times further. Okay, So we go 0.5 times 1500, same car, okay? Now times that answer squared. Okay, divide that by 8,000 newtons. It's exactly 4 times, but it's 26 meters. It's a long way. Okay? Like, that's a quarter of one straight side of the running track. That's a long way. Okay? You're not stopping in time if that happens. Okay? Now, obviously, none of you would ever go 60 to a playground. Okay? But do we often justify to ourselves, oh, it's just 10 kilometers an hour? Right? It's 50, I'll go 60. It's 110, I'll go 120. Okay? It's 30, I'll go 40. Okay? We tell ourselves that. We say, it's just 10 kilometers an hour. It's okay. It's not that big a deal. It's not that much faster. Okay? But it is. If I go 40 through a playground zone, I'm going 11.1 meters per second. Okay? If I do this same calculation, so I go 0.5 times 1500 times 11.1 squared. So when I went the speed limit, it was 6.5 meters. Now I'm going 40 kilometers an hour, which isn't that fast. It's almost double. And we justify that to ourselves. We say, 40 kilometers an hour, it's only 10. 10's not that much. Well, here's what they don't teach you in driver's ed. Speed has an exponential relationship with stopping distance. Going faster means, yes, it'll take you longer to stop. But what they don't tell you is how much longer to stop. Yep. Okay? So it's a lot. It's a lot further to stop based on increased speed. Okay? And here's the other thing, like, because we justify this 10 kilometers an hour to ourselves, the average playground zone is maybe 150 meters long. Right? So let's say that we want to calculate just how much time that 10 kilometers an hour is going to save us through that playground zone. So if I do this, 150 meters, and I divide by the speed, so let's say 150 divided by our 8.3. So if I go the speed limit, it'll take me 18 seconds to get through the playground zone. If I go 40, it'll take me 13 seconds. So I will save 5 seconds. But if a kid runs out in front of me, it'll be almost twice as far for me to stop. So when we say that 10 kilometers an hour is okay, we are accepting the fact that we will take twice as far to stop, and that saving 5 seconds is more important than not killing someone's kid with your car. They won't teach you that in driver's ed because they're afraid to say things like that. I'm not. Okay? This is simple physics, but it's also real life. And I have 2 kids myself. Okay? So that 5 seconds, if we make that decision, saving ourselves 5 seconds, which will mean nothing because the light will be red no matter what, and you'll end up stuck at it anyway, okay? That 5 seconds is the difference between me going home and having dinner with my kids or me going home and planning one of their funerals. 5 seconds. Okay? Physics. Can't beat it. You can't get past it. If you go 10 kilometers an hour over the speed limit to save 5 seconds, you are willing to accept that you will have to have twice as much room to stop. And that's under ideal conditions. If it's at all icy or slippery, that gets even worse.
That's why we have to do your braking system.
Your braking system can only do so much. It is at the whim of physics, and that is friction and speed. Yeah. Okay? I'm not saying that, having brakes, having good brakes is not important. It certainly is. Having them in good repair certainly is important. It does make a difference. But what makes it even more of a difference is going the speed limit. Right? Especially in places like that. Okay? Playground zones, school zones, construction zones. That's why speed fines double in a construction zone. There's more people. There's more chance of someone stepping out into the active lanes. Okay? That's why you're supposed to go slower in those situations. Okay? Making sense? It's work energy theorem, but it's real life. Okay. Rant over. Hopefully it makes some impact. Okay, so we've got EK equals 1/2 mv squared. Again, EK is the kinetic energy object in joules. M is the mass of the object in kilograms. V is the velocity of the object in meters per second. Okay, and we still get, obviously, the units for joules, kilogram meters squared per second squared, because this is kilograms. And when you square velocity, it's meters squared per second squared instead of meters per second. Okay, so that gives us our proper units there as well. Oh, look, I still had the calculations from the last time. 8.3, 11.1, same car. Oh, not as good at brakes, 7,500, I picked 8,000. All right, I want you guys to write this one down. We're gonna go over this as our first work energy theorem problem. Okay? Okay, so in this question, we got a rubber band stretched 0.85 meters. It's obviously not this rubber band because I can't stretch that one that far. Okay, by a force of 60 newtons. And what speed will it propel the ball when released? So, we're doing this. Don't worry, I'm not going to shoot this at anybody. Okay, but, okay, so what have I done when I pull back on the rubber band? I've done work. It's put potential energy into the rubber band. If I let it go, it'll shoot the mass out. Okay? And that mass will then have kinetic energy. Okay. So if I do 200 joules worth of work in pulling back this rubber band, how much energy will the mass have when it leaves? 200. Okay? That's work energy theorem. That's what we're working on right now. Okay? So for this one here, our givens are distance, 0.85 meters. By a force of 60 newtons. So, force. Okay, what speed, so we're looking for V, will it propel a 0.125 kilogram ball when released? So they gave us mass. Okay, so the first step in writing, or in accomplishing or solving a work energy theorem problem is obviously to write down the givens. Okay? The second step is to identify which type of energy is being changed. Potential or kinetic. And sometimes in a question like this, it's going to be one after the other, but what we're looking for is the final energy. So, what kind of energy am I going to change about this ball by stretching the rubber band? It's kinetic. That's why they're asking me to solve for speed. Anytime they're asking you to solve for speed, you're dealing with a kinetic energy problem. If they're asking you to solve for height, then you're dealing with a potential energy problem. Okay? So, in this question, the work you do is going to change the kinetic energy of the ball. Okay? You would get a mark for that. In a work energy theorem problem, you would get a mark for your givens, and you would get a mark for identifying which type of energy is being changed by the work. Okay, now our formula for work is force times distance, and I have both of those as givens. And we know that this is changing the kinetic energy of the mass. So that's going to be 1/2 mvf squared, our final speed, minus 1/2 mvi squared. What's our initial speed for the mass? Zero. Yeah. I mean, when it's in the rubber band and the rubber band is stretched like this, it's not moving. Right? It doesn't have any kinetic energy right now. The energy of this system right now is potential. When I let it go, then this thing will have kinetic energy. Okay, so right now, I can just get rid of this. And I'm left with the same thing I was looking at when I was calculating the stopping distance for a car. Okay? The work done on the rubber band is equal to the final kinetic energy of the ball. Okay? Everyone with me on that? Okay, how do I get the speed of the ball by itself? How do I isolate VF?
If you divide by it.
No, I'm going to leave VF. This is a subscript F. I'm going to leave this over here. I want to isolate VF. What do I have to do with half an M? Just algebra here, guys. Right now I'm multiplying them all. If I want to move it, I divide them. Okay, so that's all for V squared. I just want V. So what do I have to do with this whole thing? Square root it. So what I'm left with is this. The square root of force times distance over 1/2 of mass equals V. The speed at which, actually VF, the final speed of the ball. Okay, so all we've done is algebra. We haven't really done anything else other than we had to figure out which energy type was changing. Other than that, it's just been moving things around. And that's an easier manipulation than what you were doing last week with the acceleration formula. Okay, so that's going to mean the square root of 60 newtons, that's our force, times our distance, 0.85 meters, and divide that by 1/2 times the mass. All right, so I'm going to go 60 times 0.85, and then I'm going to divide that by 0.5 times 0.125, and then I'm going to square root it. Okay, so that rock is going to be moving at 28.6 meters per second when it leaves the rubber band. Okay, so the math hasn't gotten any tougher. It's still just algebra. It's still moving things around in an equation. Okay, but the context of it has gotten a little bit more complex. And we're going to spend the bulk of this week working on that. Okay, so we'll call it a day there. You will have a quiz tomorrow and it'll be on acceleration.